Crew assignments during delayed communication, human exploration of solar system surfaces. Take it away, Jake.
Thanks, Clive. Okay, here we go. Thank you. I was involved in a COSPAR meeting in 2011. It was an international group interested in trying to understand how analogs were being conducted in different countries by different space agencies and try to make sure that we aren't all inventing the same wheel over and over again. And it was an interesting meeting. At one point, it ended up in an uncomfortable discussion that was essentially finger-pointing about who was publishing more documents in their own space agency's gray literature that were unavailable to everybody else to read. And so one of the findings we had from that was that it was very important for us to make sure, within reason, we could get out as much of the information to the public so that people were aware of what tests were being run and what the results were. So I'm very happy to see several different analog results being discussed in this session today. And I urge you to stick around for the afternoon session where you'll hear a little bit more. But I also like the way the session is structured with some of the concepts, some of the data analyses that are going into planning for human spaceflight, and as well as the testing. So it kind of follows along with the motto we've used for desert rats, build a little, test a little. So with that, I'll move on. I'll be talking today about some results from desert rats. For those of you not familiar, that was Desert Research and Technology Studies. Specifically, I'll be talking about the 2011 test. Now, there are a number of different analog tests that were funded by NASA and still are funded by NASA. And in fact, both the NEMO missions and the High Seas mission are actually active right now. So the important point to make about analog tests is that none of these tests by themselves can answer all the questions we have. So each of these tests are suited to answer specific questions, and the integration of the results is really what provides meaningful information to NASA as we move forward. So with that in mind, Desert Rats in 2011 was basically evaluating different operational modes for exploring microgravity targets. So that year we basically had forced upon us a switch from definitely walking on the surface of the moon to definitely interacting with a microgravity target. And Desert Rats, for the most part, was evaluating the hardware that was being developed by NASA. So we were dealing with things like the habitat. This was called the Deep Space Habitat in the format we used it that year. So this was where crew would live, basically on a long duration mission. We were also testing the multi-mission space exploration vehicles over here. So the concept would be that these vehicles would dock with this habitat, and you could use the vehicles to ferry yourself to the microgravity targets you were exploring. Another new thing for Desert Rats that year was the concept for delayed communication. So if we're moving beyond the moon, we're now entering into an environment where there's going to be some delay in comm between JSC and the crews. So with that in mind, So we used a few concepts for how we might deal with a microgravity target. First of all, was how would the crew members be mobile? So we were testing some different scenarios. We basically made up a modified version of the SAFER, the Simplified Aid for EVA Rescue. So this is essentially a rescue type jetpack that was designed, and we were basically saying that that would be something you would need to move around on a microgravity target to interact with the target. So that's what you're kind of seeing up here as a crew member simulating that. And so we had made up a lot of rules about how fast we could move and how we would have to interact with the surface, anchoring, things like that. We also had a concept similar to the space station arm. For the test, we just called the astronaut positioning system. So in this case, the crew member was actually attached to the rover by an arm, so their mobility away from the rover was limited. So in this case, you're limited by propellant, so we had a certain number of starts and stops that we could make during without going back to the rover. And here you could move around freely as long as you were within the radius defined by the arm. So very, very quickly, we learned one critically important lesson for desert rats in that a one gravity environment is a very poor place to test microgravity concepts. So I think we all agreed upon that. And again, I say that simply to stress the importance of these multiple different analog tests. So places like Nemo or Pavilion Lake are places where you can actually simulate lower gravity environments. So if your main goal is to understand operations in those microgravity environments, you have to make sure that the physical characteristics of your analog are appropriate. But we were able to test the COM delay, and one result that Love and Regan published, which was actually results from multiple tests, was that basically any COM delay is highly disruptive to the link between JSC and the crew members. So regardless of the length, once there was a noticeable delay at all, that is very disruptive. And that was kind of one of the main things that we dealt with as we move forward. Now, one of the things that we were able to provide input about was crew assignments. So this was a meaningful result we got, and as the scientists on the team, we were very interested about the crew assignment of the scientist, or the geologist in that case. So this was an overview of some of the conditions. We had conditions 1 through 3 were related to telerobotic operations of assets, either from the rover or the dish. But in this case, it just shows a breakdown. The concept being that the microgravity target is here. In some at distance and orbit, you had the dish, and then you had the vehicle to shuttle people back and forth. So we were looking at concepts with no rover. In this case, you just had to use that jetpack to get over here, the safer. Using the rover with 2 folks in the rover and 1 person in the dish, 3 in the rover, 1 in the dish, or everybody in the rovers and heading over. Now, it's important here is that for this part of it, we were learning information that was relevant regardless of the target. So if you ignore the microgravity aspect to it, this is relevant if you're looking at a microgravity target or you're on a base on a surface that has more gravity like the moon or maybe even Mars. You still have a concept with maybe a small dish or a habitat where you're taking rovers and moving out and exploring. So despite the fact that the gravity issue was a problem for us, we still had meaningful results otherwise. So the main thing I'm talking about today is the crew assignments. So again, we tested concepts with 3 and 4 crew members, and the key finding that I think all the crew members and probably most of the team found was this concept of the IV person, the internal vehicular person. So this is the person that's either in the dish here, or that person could remain in the rover while another person or 2 were exploring the surface. Now this IV crew member had some unique capabilities that the EVA crew members didn't have. They had the ability to text message with JSC, and they had the ability to talk in real time with the EVA crew members, whether they were in the dish off-site or they were on-site in the vehicle. We rotated the geologists and the astronauts through each of these roles to try and evaluate them as best we could. Now going into this, as we had gone through the dry runs and we had prepped for the test, I think at least the scientists, but probably also the astronauts in our crew, had an assumption that the best place to stick the geologists, if you only had 1 or 2, was to put them boots on the ground. We love that term, boots on the ground for the geologists, right? Get out there and get dirty. So going in, we just kind of had that as our assumption as we moved forward. But that ended up not being what we found to be the ideal position. First of all of the crew identified this IV role as being highly critical. It's a very important position. And one of the reasons was that this IV person could handle the comm between JSC and the real-time comm with the folks on EVA. And we hadn't recognized how important that would be. This, was one of the first tests that went into that Love and Regan report about how disruptive delayed comms were. So we hadn't really recognized that, but this IV person was essentially working in kind of 2 time zones at once. They were working in the 1 minute behind schedule with Johnson, where they were balancing this communication there, and at the same time they were communicating in real time with the folks out the window or out on the object. And I can't stress how important that was, having that buffer. Now, one of the things we learned through rats, and this may be something that's reiterated by the other tests, I don't know, but in our case, we found that once the crew members went EVA or were ready to go onto an EVA, although we had a mission commander identified who was always one of the astronauts, that mission commander almost always defaulted to the geologist for science decisions. And that makes sense because they're not trained for it. So it's something you can mitigate with the training, but they know instinctively if there's a person there that has more training than them naturally in that topic, you kind of default to that person. And so this put forward a concept we talked about as the field science PI. And as the scientists who could populate a backroom in a mission, we think about being in charge of the science, running the science, but we propose a concept where the actual PI might want to be the person who's out there, who has the eyes on the ground, sometimes the boots on the ground. That's the person who's really starting to make some of those calls, especially when you move into a delayed comm scenario. Another thing we observed from desert rats was that the sample collection and proper documentation, both of the sample itself and the site prior to sample collection, is extremely time consuming. When you're spending your amount of time on an EVA, you end up eating a lot of time taking the pictures, documenting what the terrain around it was like. And this is even more so, it seemed, in a microgravity target. Now, again, we weren't an ideal test of microgravity, so other teams might find something different. But again, the point being that the sample collection and documentation, if you do it properly, is very time consuming. Now, another point that we learned, and Stan was very diplomatic about this in his publication, he noted that astronauts are very good at detailed descriptions in short amounts of time, and it turns out geologists are very poor at that. We like to talk about what we're seeing. Now, again, this is something that can be dealt with in training, but the point I want to take away from this comment we published is that the astronauts are really good at describing things, making key observations. They're very good at that sample collection and documentation step that in the bullet before I told you is very time consuming. Okay, so what was our big finding about this IV role? Well, what we found out was that the best place probably to put the geologist, if you had to make a choice, was in that IV position. Again, the time-consuming sample documentation now is being conducted by the astronaut out on the arm or on the super safer. Again, they're very good at making those detailed descriptions. This provides the geologist with a chance to look at all of the data sets from multiple crew members to understand all of that information. Now, again, remember this concept of the science, the field science PI. Just like the brain trust in the back room, now they're delayed and away from the real-time activity. You put that person into the IV role at their computer console. They can see all the information. Now they're the ones starting to make those real-time decisions, informed by the delayed comm from Houston, but you need that person to make those real-time decisions. So this effectively enabled what we call expertise multiplication. This is a term that Jose, one of my co-Is or authors, likes to use. It's a case in teaching where if you're the lead and you have several people that you can send out to look into things for you, it's essentially like multiplying your skill set at different sites. So again, within the IV role, we had scenarios with the IV in the dish, and we had the IV on the rover, and we found that the geologist was most effective IV inside the rover, because then they actually, instead of boots on the ground, they've got what we call eyes on the ground, so they're best able to make those calls. So real quick, wrap this up. The recommendations that came out from this was we did not set this test up specifically to look at this IV position, but we found within the test that the IV position was a very important role. So we recommended some further testing focused on that. One of the big recommendations we made was that unless the safety of the mission was basically in threat, was that the JSC delayed comm folks should never talk to an EVA astronaut because they have a lot on their mind while they're out there. Handle all that comm through the IV person who can essentially buffer that information and disperse it out to those folks when they have time to actually ingest the material. Again, this concept of the field science PI, keeping a trained scientist in that role. And the other last main point that we wanted to make was that if you're in these long duration missions with big comm delays, that these positions need to be flexible. So the mission commander really needs to have that ability to say, today, person X is doing this and person Y is doing that. And they need to be able to make those decisions in real time. You cannot plan this out from Earth prior to the mission going. And that's all I have to say today. Thank you.
Time for a quick question.
This seemed to be about time efficiency of getting tasks done effectively. What about the sort of the quality of the sample return in terms of the geologist versus the astronaut? The geologist notices something that's really important, eyes on. Astronaut doesn't know that.
Yeah, and that's actually a great point to reiterate our point here, is that if you have the astronaut out there, or two astronauts out there working, and you've got the geologist in the rover or in the dish, they're seeing everything through either the window or they're seeing it through the data comms that are coming back to them. And in many cases, while they were working on the documentation part, I had the picture there, holding the rock up, describing the rock, describing the setting, the geologist was looking ahead to the next several steps, and they were able to say, when that was done, okay, crew member A, you need to move 3 meters off to your right. There's a spot. I want you to check that out and pick that up. And that's why we find being IV inside the rover was more beneficial than being IV inside the dish. So I agree with you. You still want that trained expertise in the loop. But in this case, the geologist isn't burning all of their time making the descriptions, which the astronauts are very good at doing. They're thinking the science a step or two ahead and informing the astronaut where to go.
Right, I think we're going to have to move on. I'm going to